Thank you very much. Nice to be here. If you're a little bit like me, then after an hour of dense and interesting talks, your brain may also be a little bit tired. So I'll try to keep this focused on a single point mostly, or a kind of type of problems that has eluded researchers for 20 plus years. And only very recently, with the advent of large language models, there finally seems to be a way through. And that is rather exciting because it is a problem of rather significant import, as we will see as we go along. And that brings us right to knowledge graphs. Now, what are knowledge graphs? Knowledge graphs are, generally speaking, a prominent paradigm for data integration and management, but that's kind of not our main point here. Think of knowledge graphs as a type of specific database expressed as a labeled directed graph, if that you came across that term, structured in a specific way, that contains information about entities and their relations. And it can possibly be rather large. And knowledge graphs as such have been developed, have been around in order to make it easier to deal with large-scale data, multi-source large-scale data, bringing it together for multiple use cases, etc. And that's actually an area of research and technology that predates large language models, agentic AI, all the things we're talking about right now. However, if you have already heard about knowledge graphs, then it is more likely than not that you may have heard about them as something that is in the vicinity of agentic AI and large language models, particularly because there is some work that shows that they are particularly useful to help large language models in areas where they're sometimes not so good. We heard about some of these things earlier. They may just sometimes give us nonsense, for example. So having a high quality database, knowledge base, if you like, and have it interact with the large language model in some way to help improve the quality of outcome, that's something that has been done, that is being done, and you may have heard about the term graph rag, for example, which is one of the prominent approaches right now for this. But that's actually not what I want to talk about. I want to kind of go one step back here. And if we're at the stage where we see that knowledge graphs, having these highly structured databases, are helpful for this type of agentic AI, where do these knowledge graphs come from in the first place? And that brings us back to this old wicked problem, in a sense. And I'll talk about that in a second. In the context of all this, I wanted to mention that not too long ago, Samsung actually acquired a startup out of the knowledge graphs community from a very prominent research group, Oxford Semantic Technologies, a knowledge graph startup. So just wanted to say there are these connections already at hand. All right. So what are knowledge graphs? Let me get to this, and then let me get to the wicked problem. And just look at the box which you see on the right-hand side. The second row here, the second little graphics here. Knowledge graphs consists of entities and their relationships. So, for example, there could be an entity in the knowledge graph, call that a node, like Kansas City, for example. And there would be another entity like the number 516,032. And those two entities could have a relationship like these 500,000 would be the population of Kansas City, for example. Part of this knowledge graph would also be a type structure, a schema for this. Like, for example, something of type city that's above that would have a population expressed with something of the type positive integer, for example. In knowledge graphs, you usually think of this schema information. You could call this an ontology of sorts, together with the actual data graph underneath it. And now in a knowledge graph, you would have a lot of these entities densely interconnected with each other. And that actually constitutes a knowledge graph. Now, that sounds rather straightforward. It actually isn't. And let me just explain to you why it often isn't. The example I just gave you seems very intuitive, but you could start asking, what Kansas City do you actually mean here? Like, if you ask anybody in Kansas, I happen to be in Kansas, what is the population of Kansas City? More often than not, people will say, probably about 2 million. So where does this come from? Why does it say 500,000 here? And I say 2 million, or this is just a mistake I made. So what actually do I mean with Kansas City? That's the core of this question, because Kansas City can be a lot of things. Most of what I consider to be Kansas City isn't even in Kansas. There is a Kansas City proper, which is in Missouri. There is a Kansas City metro area, which has the 2 million inhabitants, for example. Now, there's another question is, well, 516,032, was that this year or last year, 10 years ago or 30? Perhaps it was Kansas City Metro 30 years ago. Who knows, without further information. All this information seems to be missing in our little snippet. Shouldn't we have things in our knowledge graph which kind of say all these things, more connections, more types, which explain this? To what level of detail would we need to go? Another statement would be, well, if what does this mean in the schema level? A city has a population which is a positive integer. Formally, you could express this in a line such as the one beneath, which would say has population, has domain city, meaning the kind of left-hand side of the arrow is always a city, and then the next thing, range, would be a positive integer. Right-hand side is always a positive integer. But then you have the problem that other things have populations as well. For example, state. So kind of, is this now a problem or not? What do we actually mean with this statement? Well, there are standard languages for this, which have been around for 20 plus years, which tell you what exactly you could use and what not. But it probably explains already that you need a little bit more careful if you kind of want to be more exact in what you actually want to express. So for this reason, in particular on the types like city or positive integer, ontologies, schemas, allow to express formal relations using formal logic. Like, for example, the one expressed in the next line saying, in English, every city has a population that is a positive integer, which seems to be a statement that makes sense. But we can ask more questions, like, for example, how did you come up with this number? Nobody actually counts people in cities. Every number you get as a population number is a number somebody arrived at using a statistical approach to estimating the number. So somebody who may be interested in looking at this in more detail rather than a kind of just a glance at numbers saying, what's the ballpark of population of Kansas City? But somebody who may be a demographer, for example, may want to know, so what actually was the statistical method used here? What is the base data that was used? Where is that? Shouldn't that all be listed in the knowledge graph as well? Well, for that person, perhaps. So you see that knowledge graph isn't equal to knowledge graph. So knowledge graphs are more self-explanatory. They keep more information. Some are more granular. Some are more coarse. There's different reasons for having different knowledge graphs. And making a knowledge graph in particular at a kind of high quality level that is rather granular needs expert knowledge. Like, for example, if I would like to also list the statistical information, statistical method, how they were used, inputs, outputs to that, etc., algorithms, then the graph is going to get complicated. And I probably need a statistician to explain to me what all that means. And perhaps not only a statistician, but probably also some other people who understand about populations and how these are assessed in the real world and how surveys are done and all these kind of things. So, and that brings us to the wicked problems. While these knowledge graphs are really helpful, and this has been shown before LLMs came along, they're helpful for large-scale data integration, for getting the data together and then do something with the data, answer questions, complex questions if necessary. Then making these knowledge graphs and the corresponding schemas is very expensive. It's primarily very expensive because it needs expert time. It needs experts from all the relevant areas to come together, discuss with each other what is a good schema, discuss with each other what is a good structure for the knowledge graph, and then realize the knowledge graph. The technical realization of the graph afterwards is actually much easier, but designing the thing in the first place is a lot of work. So, and of course, now we have a research area. Actually, the semantic web research area is where this all comes from originally, which is 25 years old. And of course, computer science researchers have looked at automating or semi-automating creation of knowledge graphs, other engineering tasks around knowledge graphs, like, for example, integrating knowledge graphs, taking two or more knowledge graphs, putting them together into one big one because you need the data together, And how can we actually save time and effort doing that? And it turns out that that is hard. That is really, really hard. And before the advent of large language models, it was kind of not really clear when we will ever make a dent into that big problem. All right. And now enter LLMs. And now I'm not bringing this back to LLMs because I want to talk about how knowledge graphs can help LLMs. We have a lot of research around GraphRag and other methods, which show that, yeah, there is significant promise. And of course, the research has to stabilize. I'm looking at the other problem. Where do we get the knowledge graphs from? And can we actually use LLMs to make these knowledge graphs, which we can then use for whatever purpose we want to? And, well, at the first glance, it seems clear. LLMs really can act as a type of natural language-based database, which you can query. You ask it, you get information back. The information is more often than not reasonable. And then also we know that it is possible to receive structured outputs from these large language models. Like, for example, in coding assistance. Coding assistance seems to be a thing that everybody accepts now as, yeah, this is helpful just because they experience like that. I actually do not know if there's any formal studies looking into that, but it seems clearly helpful. So likewise, one could look into this natural language-based databases that large language models are and say, give us structured output in the form of knowledge graphs, for example. Or I give you two knowledge graphs, use your common sense natural language-based database to integrate these two knowledge graphs into a bigger knowledge graph. And it seems that that should be possible. It should be possible to help humans do that, such that not as much time and effort of humans will be required to do that. Well, in this big theme, there's different sub-problems which turn out to be hard. One I mentioned already is making a good schema, ontology or schema modeling. Actually constructing a knowledge graph based on a schema that has already been developed. Some people call this ontology population. And another one would be, as already mentioned, the integration of knowledge graphs via ontology integration or alignment, a mapping between ontologies. And I'll particularly talk about the last part because I think it's the clearest case where large language models can help in the context of what has been done so far. All right, so let's see what some issues may be that crop up in this context. And the issues really are issues that, well, some of the issues, at least, that we know large language models have if you want to apply them to something where quality is actually important as an output. Hallucinations are one of them, or general output quality. As Sobral also mentions, they often give you good stuff, but sometimes they just give you nonsense. Scale may be a problem, prompt size. If you talk about knowledge graphs, we released, I believe, probably the world's biggest geo-knowledge graph a few years ago with, I believe now about 20 billion node-edge node pieces, triples as they call them. So that's big, right? You can't easily just feed that into a prompt. So you need to deal with that. And then, of course, knowledge graphs may also be about niche themes because you may want to answer some very specific questions, even more specific than what are methods to assess populations of cities, for example. So, some may be addressable, of course, and I'll come to that on one of the later slides. But how exactly actually can we get towards addressing them? And what are key bottlenecks we can look at here? All right. So the example which I want to talk you through, which is one of the problems in the context of ontology engineering that has been evading researchers quite a bit, is in the context of ontology alignment. This is about the following scenario. You have two knowledge graphs with two ontologies, and you would like to map the data from one graph to the schema of the other graph in such a way that the two graphs become integrated. Now, there's a lot of things involved in this, but one of the things that you want to do for that is essentially map the schema to the schema. And there's an example at the very bottom here. This is a rule, a double implication rule. Think of the first line of the rule in the bottom 3 lines. The first line here as an expression coming from the first ontology. It talks about awards. This would be funding awards, project, for example, research project awards. X would be such an award, and it would have a co-principal investigator, say, which would be given here by a variable z. Now, the other 2 lines are an expression, again, a logical expression, which pertain to the second ontology. X again here, but it would be called a funding award in this ontology. It could also be called completely different, but let's assume it's called funding award. This funding award provides an agent role Y. This agent role is a co-principal investigator role Y, which is performed by Z, again, our co-principal investigator. If this seems weird to you, kind of why is there this chain of things? That's actually a very common technique in knowledge graph modeling, because that gives you the opportunity to attach a lot of contextual information to the pieces, which may help you understand, for example, that Kansas City is the metro area or something else, for example. So ontology alignment is about feeding these 2 schemas, these 2 ontologies, to a system, hopefully an LLM in our case, and asking it to actually come up with this rule, which gives us the mapping. Now, this is a rule which actually comes out of a benchmark, which is already a few years old, precedes the LLMs, and this is an example for a complex mapping. Simple mappings are just about finding types like award and funding award and saying they should be equal. But of course, the more complicated, the more important problem is to actually find all these mappings. Now, before recently, essentially finding complex alignments was virtually impossible with automatic means unless you have really strong assumptions, like, for example, a shared knowledge graph with 2 schemas, which are just not really realistic for realistic scenarios. So essentially, we didn't really know how to do it. For the simple ones, which just look at types and mapping into each other, the situation was much better. Don't need to talk too much in details here. Mostly string similarity metrics actually did a lot of the job, and now LLMs can actually do similarly well on these simple alignment problems. And that's fine and that's good, but we want to look at the complex one. The example I was giving you is actually out of a benchmark called the GeoLink benchmark. This is out of a real integration effort of 2 ocean science databases, large US ocean science databases. And so we had then at some stage these 2 ontologies, and we mapped these 2 onto each other without even thinking about making a benchmark. And only later on we said, well, okay, we can just release it. Now, if you take this benchmark with these, I believe, 109 rules or so, which we had there, so it wasn't terribly big, just 109 rules. Also, the ontologies are not terribly big. We're probably talking about dozens of classes. And you just feed them to a large language model and say, give me the rules, then essentially doesn't work. We even gave it a slightly simplified scenario. We didn't ask for the rules. We just said, well, if we give you, say, the left-hand side of this rule, just the kind of the top line here of this rule, and say, this is from the first ontology, then give me only the predicate names from the second ontology that we need to assemble the rule. That's a simple problem, right? We don't ask for the rule just for the pieces which need to be assembled, but that would still help a ton because you give that to a human and the assembly is really easy. So we asked the simpler problem to LLMs, and it turns out that they kind of gave us about 4.5% correct of what they told us. That is clearly not enough, even for semi-automation. That's just not helpful. 5% is just not helpful. So what can we do? Well, and in comes a second idea, and that's the idea of ontology modules. I don't want to go into detail, just focus on the red here. Ontology modules are essentially a method to divide and conquer. You think of an ontology, the schema in that case, and then by proxy also the knowledge graph itself, as a set of parts which are interconnected parts of the graph or the ontology, which kind of makes sense for a human. And let me just give you a little graphics here first. This is essentially a depiction of a schema There's no logic here. Underlying there is actually logic. This is just a simple depiction of types and how they can be related to each other. And this is actually an example from a logistics, a supply chain tracing ontology in the knowledge graph, which we actually did with application partners. And for example, down here on the left, there's events, which are events important to the tracing in a supply chain. Like, for example, every time you have a data point, like, for example, the container actually changed hands or changed owner or was sold, things like this. And each of these events, you get a record. So if you have a string of these records assembled in a trajectory, the trajectory is up on the upper left, while the event is on the lower left. Then you can actually put these points together in a trajectory. In the middle, there would be a piece which gives you the container into which the goods are actually packaged, for example. And there's more of these pieces on the right. And well, these gray boxes, which I just pointed out, trajectory, container, or event, these would be modules. So each module of this big schema talks about something that makes sense for a human expert. It makes sense to talk about supply chain events. It makes sense to talk about trajectories, about containers in this context. And so the whole ontology, and therefore the knowledge graphs, falls into these different pieces. Now you would say, well, that's kind of trivial. That makes sense. Perhaps you do. Well, the reality is that for 20 plus years, ontologies have been modeled without doing this. You just get the big thing, the big interconnected graph without any internal structure. Although, of course, the people who would initially model this ontology, they would usually have this internal structure in their heads. It would just not end up on the ontology. So the change here is to say, well, let's not get rid of that, but rather when the ontology is made, let's keep this modular structure so that we can make use of it. And making use of this in the context of ontology alignment actually work like a charm. So a module is a part of an ontology that constitutes a conceptual unit in the eyes of a domain expert, like a trajectory, for example. And yeah, there's tools to deal with them, etc. Now back to our benchmark, the GeoLink benchmark. What you see here in the upper part is a diagram, and this is not a diagram for the ontology now. Each of these nodes here is actually a module, and what is shown here is primary relationships between these modules. So we have about, 20 modules or so, or 18 in this ontology. And 18 is much better than several dozen. So what we did now is we used exactly the same problem, namely the find us these pieces for the alignment mapping, for which one example we saw earlier. But we now made that a double stage process. The first one was we gave it again part of the map of the rule from one ontology, and then gave it a list of the modules of the other ontology and asked the system, which module or modules do you think you will need to find the pieces for the mapping? And the LLM told us, well, for this one, we need the agent role, for example. And then in the second stage, we fed the LLM only the modules it requested together with the original question, and it came back with its answer, namely the pieces that the LLM was claiming we would need to make the rule. And it turns out that we went up from 5% correct to 95% correct. And that was quite breathtaking. I mean, we expected that it would work better, right, than not having the module. But honestly, I did not expect that we worked like a charm. In the meantime, we replicated this experiment on a second benchmark. That's the only two benchmarks we have which have modular information at the moment. The other benchmark is completely different. It's about the history of the slave trade, also very, very differently structured, and the results are essentially the same. So that was quite breathtaking for me. All right, so I think I have 4 minutes. So there's additional evidence that modules are helpful for LLM-assisted knowledge graph and ontology engineering. I just talked about ontology alignment because I just kind of, for me, was the most striking example. We also looked at ontology modeling. We looked at ontology population. We also had initial indications that modules are really helpful there as well. They essentially help you to chop down the problem, to do the divide and conquer. All right. I promise to come back to some of the obstacles which you often have when doing something with LLMs and how they could be overcome. Human in the loop is one of the things that can help with hallucinations, for example. Of course, 95% is not solving the full problem, but 95% will go a long way of making this very expensive task much easier and therefore much more cost efficient by just kind of solving 95% of the problem, throwing the rest at the human, probably with some nice interfaces to do that, which of course need to be developed. General output quality, again, that can be addressed by using good ontology modules or something very related to that, which is design pattern libraries. For example, when we want to make good ontologies, don't start from scratch, use modules from other ontologies, which are known to be good to make your new ontology, for example. Scale, the divide and conquer approach using modularization, as I just talked about, I think can be a key ingredient to this. And dealing with niche themes, like you need a knowledge graph on a very specific niche theme, combinations of fine-tuning, human in the loop, specialized ontology design patterns and modules may be a way to address this. We do not know at this time. This is all ongoing work. So, conclusions. LLMs bear a significant promise to accelerate knowledge graph and ontology engineering by assisting human experts. I think this is clear now, and that was kind of the hope the community was following since LLMs came along, and I think we have clear indications now. Of course, the details need to be worked out, and it's a very good time right now to look at that, because there's broad breakthroughs to be had here, and you want to be ahead of the curve, of course. Exact methods need to be established, and there's also seem to be clear indications that divide and conquer methods, ontology modules in particular, may play an important role in obtaining useful LLM outputs in some cases. So, going back to the very beginning, I was talking about knowledge graph engineering using LLMs to accelerate and essentially also make cheaper knowledge graph engineering, meaning the creation of knowledge graphs and the integration of knowledge graphs. Knowledge graphs at the same time are currently being looked at as major ingredients in agentic AI, using knowledge graphs to, for example, bring more grounded truth to LLM computations to make sure you get more quality output. There's significant indications that that is exactly happening. So closing the loop here in a sense. Thank you very much. I'm at the end of my time and I'm happy to take any questions.